then just unmute yourself and speak. Luca, go ahead.
Okay, so thanks a lot, Christine. Yeah, so before starting, actually, I wanted to thank the whole, I don't know, EUMETSAT team and people who worked on the creation and sharing of the Data Cube, which I think it's a really, really nice tool and instrument that you're sharing with us. And yeah, and also thank you, Christine, for the help and support in the past few weeks. Yeah, so having said this, this presentation is about this work or idea that I've started working on in the past few weeks. That is the downscaling of the CCI soil moisture product to an intermediate spatial resolution. So 0.05 degrees, that is approximately 5 kilometers. It's a rather high level presentation, so I'm not going too much into the details of, let's say, the technical implementation, but yeah, if you want, we can also talk about that later. Yeah, so just some introduction on the reasoning behind this work. So as you probably know, soil moisture is a key variable that affects a lot of climatological and hydrological processes. And in this schematic representation, you can see just some of the processes where soil moisture is involved, being at the interface between the land and the atmosphere. Also, soil moisture is strongly related to vegetation and crop development and productivity. And this is clearly shown, for instance, in these plots here. So these maps here are the Pannonian Basin, that is the eastern part of Europe. And on the left side, you can see some drought indicators, where red means very dry, blue means very wet. On the right side, you have some vegetation indicators, where brown means very poor conditions, green means very good and healthy vegetation. And here, this highlighted period, for instance, is the 2012, where we recorded some pretty drought conditions over this area, and this was also pretty well reflected in the spatial patterns of vegetation. And also when you look at the temporal development of let's say, drought indicators, among which soil moisture and vegetations, there is a pretty strong correlation and agreement between the two. So yeah, soil moisture is very important. And yeah, however, soil moisture is very, very variable, both in space and time. And when we look at the spatial patterns, these are quite complex, and also the factors that govern the spatial distribution of soil moisture change with the scale we are looking at. So in this figure here, kind of represent this concept where we see that the, let's say, small scale, let's say field scale or small watershed scales, the main dominant factors affecting the spatial patterns of soil moisture are the local vegetation differences, and then topography and soil properties. But when we move to larger scales, so when we consider either large catchments or regional scales, then we have a different set of variables that are behind or that govern the soil moisture distribution. And these are mostly meteorological forcing, land cover patterns, and so on. And for this presentation, I'm mostly interested at these rather larger scale variables here, so meteorological data and land cover patterns. Okay, we can monitor soil moisture through remote sensing, and particularly with microwave sensors. And there are quite a few satellite missions and sensors that are that have successfully recorded soil moisture. You might be aware of the SMAP, SMOS, Sentinel-1 missions, and so on. Here, I decided to focus on the ESA CCI soil moisture product. That is a combined product. So basically what it's done, it takes soil moisture products from all of these satellite missions and combines them to provide a single harmonized soil moisture product, which has the advantage of having a better spatial and temporal coverage, and also like the time period that it's covered is much longer, and in fact it provides data for over 40 years, so allowing climate analysis, for instance. When we look at the soil moisture products, most of them are characterized by a pretty coarse spatial resolution. So also the CCI soil moisture products has a spatial resolution of approximately 25 kilometers, so it falls around here, and a daily temporal resolution. But when we look at the, let's say, requirements of soil moisture information, depending on different applications and fields, you see that most of these applications require daily observation with a spatial resolution in the order of few kilometers, or actually even higher than 1 kilometer. So with this work, I'm actually trying to get some soil moisture information around here, so with a daily temporal resolution and a spatial resolution of approximately 5 kilometers. But yeah, as I said, the CCI soil moisture comes with a spatial resolution of 25 kilometers. So how to bridge this spatial gap possibility is offered by downscaling. And the main concept of downscaling is to take some, let's say, coarse resolution soil moisture data, and then also some ancillary information which are available at a higher spatial resolution. This can be either static over time, so soil information, topography, or dynamic. So we can have vegetation information, surface temperature, backscatter, and so on. And then combine all of this information into a downscaling framework, which can be either a physically based one or a data-driven machine learning approach. And the main idea is that at the end we will have soil moisture information at a higher spatial resolution. And in this nice review paper from a couple of years ago, the authors compared different downscaling techniques, and basically they concluded that the machine learning based techniques provided better results. And here you see the results of different downscaling techniques. The blue one is the machine learning based, and you have the R-square on the y-axis and the root mean square on the x-axis. And basically, the ideal or the best performance would be obtained here at the bottom left corner, and the machine learning that is the blue is kind of the closest down here. So basically, there is pretty great potential of exploiting machine learning for this task. So this is kind of the rationale behind the work. And now what I've done so far, I decided to take some data sets from the Data Cube. I choose the global radiation, the direct normal solar radiation, and the leaf area index. From the data cube. In this instance, I only consider the kind of near real-time products and not the historical data. And I also included the land cover. I'm not going into the details, but yeah, I took the Korean land cover, which is available at 500 meters, and I resampled to the same 0.05 degrees resolution and accounted for the percentage of the first level of classification. So there are 5 different levels. There are agricultural, natural, artificial, wetlands, and water. So that they provide this kind of information. And yeah, also we have the soil moisture from the CCI initiative. And yeah, these are
Luca?
just some.
Yeah, I'd have a question, just a quick one. The land cover data here is from the Copernicus Land Service, or maybe I missed that. Where did you get that from?
Yeah, it's the Korean land cover.
Okay.
So yeah, the Copernicus, yeah.
Mm-hmm. Yeah, thanks.
Yeah, so these are just some how the data look like. So here on the top left, we have like solar radiation from the data cube. Here, bottom left, I think it's the fraction of agricultural areas from the Korean land cover. And here on the right side is the CCI soil moisture. So you see that the resolution is much, much coarser with the CCI data. And in order to then also evaluate my approach, I consider the Mossmania network, which provides in situ measurements of soil moisture over southern France. So basically my study area is around this network here. And you might have noticed that the overlapping periods among all the data sets is these 2 years, so 2018 and 2019. So that's my temporal interval that I've considered now. And just very quickly, I'm not going into the details here, but I selected random forest as a first try for downscaling. And basically, I provide all of those data sets, so the global radiation, the direct normal solar radiation, leaf area index, and land cover, and CCI, and all of these data sets are fed into the model, and then I try to predict soil moisture at a spatial resolution of 0.05 degrees. I use 2018 for training and 2019 as a validation period, so that they are completely independent. Just some very preliminary results from the random forest. We can have feature importance, and this basically shows that the highest importance comes from the soil moisture, which is kind of expected because this provides the drying and wettings, dynamics, which are not represented by the other data sets. And then, quite surprisingly to me at least, I found that the land cover has a pretty high importance. And then it's followed by the vegetation, so the leaf area index and the meteorological data. Just something that I want to mention here is that the land surface temperature, which is a pretty critical variable for determining the soil moisture variation, has not been included here. And I think that with the land surface temperature information, also this bar plot. So the feature importance might change a bit. And yeah, here is just an example time series of the retrieved soil moisture of the, let's say, downscaled soil moisture here at the bottom in red compared to the CCI soil moisture in the top time series in orange, while the black dots represents the in situ soil moisture from the Smosmania network. And yeah, they have a pretty good agreement between each other. And yeah, but in general, when I look at the whole results, so this time series refer to only one single station. And for instance, here you see that the correlation slightly increased from using the, let's say, CCI at 25 kilometers compared to the downscaled soil moisture here. But when we look at all the results for all the in situ stations, we see that the downscaled soil moisture, there is the blue box plots here, are slightly worse compared to the original CCI data set. There are these orange boxes here, both in terms of correlation and root mean square error. So yeah, this is something that should be improved. So yeah, as I said, these are just some very, very, very preliminary results, and there is a lot that I have to address and to look into. So for instance, this map here represents the downscaled soil moisture. So this is the southwestern France of the study area, where you see these very patchy patterns where, you know, the small cell grids are the downscaled ones, while the larger blocky patterns are driven by the original CCI data. So this is something that needs to be kind of smoothed and, you know, considered. And also another problem that I've not addressed yet is the consistency of the downscale data, in the sense that all of the, let's say, high resolution or 5 kilometers downscaled soil moisture within the CCI soil moisture pixel should be, so the average of the downscale data should be identical to the soil moisture value of the CCI data set. And that is not the case at the moment. So this is shown by this scatter plot here. So where you see that the data are pretty close to the 1-1 line, but there are quite some outliers, and that this should be really completely overlapping in the ideal case scenario. And then there are also some other points. So as I mentioned, I only consider 1 year for training and 1 year for testing. So I think that this period should also be extended. And at this point, I've not really considered the different quality flags or controls that are provided, which might remove some outliers, and also maybe I should include some additional masking. And one last point, which kind of repeats what I mentioned before, is related to the land surface temperature, which I think is a really important variable for this analysis. And this still needs to be included. So these are the results I have so far, and the idea that I want to bring forward. So yeah, if you have any question or doubt or suggestion, yeah, I would be happy to hear about